Last session about HPC and parallelization. Interesting topic. Our first speaker is Bartosz, and he's talking about quantum chromodynamics and simulating them in a flexible way on heterogeneous supercomputers. Stage is yours.
All right, thanks a lot. Hi everyone, I'm Bartek. And the talk today is a bit of an experiment because I'm going to focus on something somewhat unusual. So this is work done or relying on contributions by many people from many different places, and I wanted to make these contributions visible somehow. So I could tell you several different kinds of stories. I could tell you some background on the science and motivate the development that we do. I could talk about the HPC aspects. I could talk about the structure of the software that we write, and to some extent this is what I'm going to do. But I really wanted to focus on interactions between people and stakeholders, which I'm finding more and more important. So on the one hand, there's people like me, researchers with some physics goals. Then there are hardware vendors who, of course, have their corporate strategies behind them. And then there are HPC centers which provide a service to the scientific community. And the thesis of this talk will be that ad hoc interactions between the above groups, at least in our case, have enabled much of our recent research. All right, so I spend a large part of my time in these interactions, and I found them to become more important over time. Fortunately, the presenter has some problems. And this looks very much like open source projects. And as I will show you, some unexpected and interesting things happen as a result of these interactions. So, as I promised, I want to motivate the science a little bit. Let's ask ourselves the question, where does the mass of a proton come from? Maybe we know that a proton is made up of two up quarks and one down quark. The quarks interact through gluons. The gluons are massless. The quarks are very light, so a quark has a mass 300 times lower than a proton. So where does all the mass come from? Well, it turns out that when you pull apart quarks, the force between them increases very much. And it turns out almost all of the mass of a proton comes from this potential energy or from this binding energy. How do we understand it? There's a quantum field theory called quantum chromodynamics. This is its Lagrangian. I'm not going to go into the details, don't worry. The only point I want you to remember is that QCD cannot be solved analytically. The solution is lattice QCD. What we do is we confine QCD to a finite box. We discretize the theory into a 4D space-time lattice. We put the quarks on the vertices of these lattices, and then the gauge fields are links. I'm pointing out the gauge fields because I'll repeat that name quite a few times in the talk. And then we can simulate the system like a statistical system in statistical mechanics with a particular Boltzmann weight. And we generate observables of these gauge configurations, and observables are then just statistical averages with statistical errors. Now, this is easy to write down, but hard to solve. It turns out to be a numerical grand challenge. And generally, you can split the job into three different pieces. On the one hand, you have the ensemble generation. Then you have something which you can think of as sampling the vacuum, colloquially. Then you excite the vacuum, you create particles, and you destroy them, and you analyze the correlations between them, and then there's analysis. I will talk only about the first two stages. The analysis stage is an interesting topic in and of itself, especially when considering fair data and fair software. So the first stage, generating the ensembles, it's a Markov chain process, so it's sequential, which means that what we want is for it to strong scale well. We want to run on as many CPUs or GPUs as possible. So there's a capability problem. And then the second stage, where we actually extract the physics is contained in correlation functions. These are mathematical objects which quantify the interactions between particles that are created and annihilated at different times. There we have to compute these so-called quark propagators. These are inverses of a very large, very sparse matrix. Out of these propagators, we build operators which excite the vacuum. So they create a proton and they destroy it, and then we can analyze the correlations. These problems are kind of naively parallel, and we want to run them on as few resources as possible, but increasingly the analysis chains here or the calculational chains here are so complex that you actually need capability resources as well. To put it into numbers, we use billions of core hours of computing time over the course of one large project, or tens of millions of GPU hours, and we need petabytes of long-term storage. What about the community behind all of this? So we are theoretical physicists related to high energy physics, particle physics, hadron physics, and so on. The yearly Lattice conference attracts about 500 to 800 people, so the community is quite small compared to others that have such high computational resources. The state of research software engineering in Lattice QCD is lackluster maybe. So traditionally, lots of user developers writing our code. The algorithms traditionally were quite simple, which on the one hand means that we are often trailblazers on the new architectures, but we often adopt ad hoc solutions as production code. Since about 2014, algorithmic complexity has been growing, and we have, just like everyone else, been hit with HPC heterogeneity. So on the one hand, we want to keep pace with hardware diversification. We want to keep our current production stacks running. We want to somehow integrate short-term postdocs and PhD students, these are physicists, not developers, into this process. And we have to, of course, do continuous integration on the hardware that we want to run on, which is either expensive or mostly unsupported. Although those of you who've been in the continuous integration session may have learned that there is a lot of progress on the side of HPC centers here. And I've personally found that RSE culture has been quite difficult to establish in this community. Some examples of Lattice QCD codes are here. So you can't really see it, but these have between 14 and 40 contributors, not all of whom are active developers, but that's about the size that you have to expect. And I will talk just about two codes. So the first one is TML QCD. This is our workhorse code. This has a 20-year history. It's about 140,000 lines of C and C++. It's a hybrid Monte Carlo algorithm for so-called Wilson fermions. It's OpenMP and MPI parallel. And one key decision that we made a while ago is that instead of writing everything ourselves, we either create libraries or we extend existing libraries. So we have MPI.io through our own library. We support AVX512 through a library developed by Barl and Joe. We have an advanced multigrid precondition solver. And we have GPU support, crucially, through the CUDA library by NVIDIA. Now, CUDA is a very interesting project. So this was started as a project by Kate Clark at Boston University some 15 years ago. It's about 200,000 lines of C++, CUDA, and now HIP and other things. There are many interesting technical properties, which I'm not going to go into details of. The most interesting aspect for us is that even though it's an NVIDIA project, there are many backends for hardware from other vendors. It's very high performant, has a very open development model, so contributions are always welcome. There's lots of support. It's out on GitHub, even though it's a essentially commercial project, but it has an open license. Very high test coverage. Contributions must follow certain coding standards and provide tests. And there's a C interface, which is very important because many Lattice QCD codes are written in C, including ours. And over the past couple of years, the CUDA library and the interaction with its developers have been really essential for us. So what kinds of interactions am I talking about? On the one hand, we have us as researchers. We have the computing centers that we rely on to provide us this computing service. And we have the vendors who may provide libraries and hardware and so on. I'm going to start with the interaction with the CUDA developers. So we are a quite small collaboration. And if we were to implement all the kernels ourselves, we would have a somewhat hard time to reach the same performance. And we would need to be many more people to maintain this over time. So instead, we have this fruitful interaction through GitHub, email, video calls. So for instance, we find some performance regression in some part of the library, we go on GitHub, open an issue, and 20 days later, the performance regression is resolved in general. Or we want to develop a new feature. So again, open a pull request, and then it takes us quite a long time to do this. But then in the end, the CUDA developers help us polish and merge the thing into the mainline of the library. So there's a very, very cool interaction with them. And then on the other hand, we have computing centers. So I'm going to talk about two things that we did together with Joule Supercomputing Center. On the one hand, I'm going to talk about the Joule's Booster Early Access Program, and I'm going to talk about what triggered this talk, which is a very interesting long-term support issue. I'm not going to talk about co-design, which is something that is going to become more important as we go on. In late 2020, Joule's Booster was installed, and from September 2020 to January 2021, JSC had an early access program. There was a Slack channel for quick exchange. The documentation for the system evolved as the program was going on, and the machine was open step by step. So as more nodes became available, it was possible to provide real-time feedback to the admins, to the user support, and this produced a very valuable interaction with JSC and with other groups as well who were participating. So at a very basic level, we exchanged compilation recipes, of course. But one interesting thing that came out was understanding the pinning topology on these nodes. So Joule's Booster nodes have 4 GPUs connected by NVLink. Then you have 4 network interfaces, and you have 2 CPU sockets with 4 NUMA nodes each. And the interesting thing is that not every NUMA node is connected ideally to every network interface, and the numbering is quite inconsistent. So in order to really be fast, you have to pin to the correct NUMA nodes and make sure that you're not using memory from the other NUMA nodes. Depends on your code, but that was one of the things that was figured out quite early on. And during this early access program, there were quite a few issues with the PCIe firmware, which were resolved over the course of this program. As the machine stabilized, we got access essentially to all of it. And this, on the one hand, was a large-scale test of the machine with basically production-level jobs. And it allowed us to produce a massive number of calculations, which would otherwise not have been possible. And this enabled all of these publications and further computing time applications and so on. And then in January, there was an online symposium where we exchanged our experiences. And we found that this was a very, very valuable experience. And we're looking forward to the Jupyter Early Access Program, which will be a little bit more formal, but will certainly also be quite interesting. And now to the final thing that I wanted to talk about was this long-term support request, which actually led me to prepare this talk. So in May 2022, I noticed that for a particular problem size, on a particular number of nodes, 25% of my jobs were taking nodes down. And of course, neither I am happy, nor the computing center is happy, because they have to reboot the things and check them. But it was quite strange, because the same executable with different problem sizes on various node numbers did not show the issue. We tried replacing the software stack, etc., etc. Nothing was helping. I created a reproducer, and then Ahmed Fahmy from the support team was able to reproduce this and noticed, okay, there's a CPU error being triggered by our code. Then another, Damon Alvarez, reached out to ATOS, NVIDIA, AMD, suspecting a weird hardware problem. And in December of 2022, it was concluded something is sending a packet in the PCI bus that the CPU does not know how to handle, and as a result, it crashes. Lots of waiting ensued, especially for ADOS, AMD, and so on. In the meantime, JSC was able to reproduce the issue on a different machine, also with AMD CPUs and GPUs, but a slightly different architecture. There was lots of internal investigation as 2023 rolled along. We also did some tests on Meluxina, which is a machine with a similar architecture that we were running on, where we didn't have crashes. And then in October of 2023, JSC was so nice to provide me with a dedicated reservation where my jobs were running while they were monitoring the hardware sensors for a week. And then they concluded, we noticed earlier that the crashing nodes experience a low voltage value, almost idling, for one or more very short time intervals on one of the two CPUs of the crashing node, and then at a later point the node crashes. The low voltage readings do not show on any of the other nodes allocated to the job, except for the crashing node. And then it turned out, okay, a simple workaround, use the GPUs in low power mode and use the on-demand CPU governor for whatever reason. And we're now waiting for AMD to provide a permanent fix for this. We will see. So I didn't expect to find a CPU bug. And I think this close interaction with the support teams on these complicated systems is absolutely crucial. And this also means that the HPC teams need to have enough people and enough funding to be able to do this. And with that, I wanted to conclude. So thanks to everyone who was involved from these different places, and to everyone that I have forgotten, sorry. There are many people who contributed explicitly or implicitly, and thanks a lot also for your attention.